Okay, off we go. So we talked last time about spherical coordinates, and let me just remind you real quick. We have this idea of doing a pullback through the spherical coordinate conversion formulas, thought of as a change of variables function, right? And yeah, it's a pullback, and yeah, technically you should, there is a pullback domain, but instead of drawing that and slicing it up as usual, we can infer what the slices are by just kind of pushing forward, if you will, what those slices look like, and this is what they look like, and then likewise for the phi slices, etc. So let's see that in action. It's, by the way, of course, very analogous to what we've already done for cylindrical coordinates, what we've already done for polar coordinates. Okay, so here's our first example. We're going to look at this domain. It's the ball of radius A centered here at A on the z-axis. So this is not centered at the origin. It's kind of sitting on top of the origin, if you will, in the xy plane. Okay, so theta slices first. That's what a theta slice looks like. Now, geometric appeal, you just got to look at the picture, think about it three-dimensionally, let the picture be your guide, and this is what one of the slices looks like, right there. Right, and now again, another geometric appeal. This is what those slices look like, but overall, we're going to get that sort of a picture all the way around this solid. You might say this solid kind of surrounds the z-axis, and so these slices go all the way around, and thus 0 to 2 pi for our theta bounds. Everybody with me? Everybody happy? Okay. Now, y'all recall, I'm sorry, I forget what I've covered in one class versus another class. You won't recall this, I haven't said it yet. I think the following is a good idea. You don't have to do it. This is just a visualization tool. We've got our existing theta slice, and we need to look at that theta slice, and we need to do some analysis in this slice and infer things about angles. And here's the awkward sort of reality here. This angle, like that, I know that in space that's a right angle. But in my picture, it looks like an obtuse angle. Everybody see what I mean? It's a little bit distorted by the fact that we're not looking at this straight on, right? We're looking at it kind of at an angle, and so sometimes right angles look obtuse. Sometimes right angles look acute. It's a weird way to try to do business, right? Now, if you're really good at visualizing things three-dimensionally, maybe you can kind of visualize your way around that, and that's fine. But I'm just going to point out, for your consideration, if you just redraw that slice in such a way that you're looking straight on at it, and now notice that same right angle. Now it looks like a right angle. Everybody see what I mean there? It just makes life a little bit easier. You don't have to do it, but I'm gonna do most of my examples doing it this way just to make it a little bit easier to visualize. Okay, so with that in mind, and looking at our theta slice is what we've already drawn there. Let's think about our phi slices. That's a phi slice. Keep in mind, phi is this angle, right, measured off the positive part of the z-axis. So a phi slice looks like this. In particular, it's this kind of line segment like that. And where the first and the last, well, I think you can see 0 is going to be our first phi slice. And then from there, phi will increase, and phi keeps getting bigger and bigger, and these slices get smaller and smaller until the very last one is when I get to the horizontal. And that's a geometric appeal, right? That's kind of what you might call the tangent direction to the bottom of the circle down here. And that's pi over 2. What do you think? Is that cool? Everybody's happy with that? Okay, so pi over 2. All right, and as usual, then we're going to now fix phi and theta. So I'm looking at a phi slice of my theta slice, and we play the usual games now with rho. Rho is going to start there. Wait a minute, what is that? Don't forget. Let's see if I can, We're actually looking at a phi slice there, and this first value of rho is actually there, which is the origin. And at the origin, we already know what rho is. Rho starts at 0. And then now the next part, and this is the hard one, rho is going to end at that point. Don't forget what we redrew this from. That point, that point actually means this point, which means it's on the sphere. And I need to know the equation for that sphere. And so, okay, you're going to have to use the given particulars, right? We know the radius, we know the center, and you can write down the equation x squared plus y squared plus z minus a squared equals a squared. And then, keeping in mind that we need that in spherical coordinates, you've got to go back to chapter 1 and remember how to convert equations, rectangular equations, into spherical equations. We did a couple of examples of those, and it's a process. And when you go through that process, you will get that. And keeping in mind that we are looking for a rho bound, you solve for rho, and that gives you your upper rho bound. Everybody see how this works? Notice it's still, just like every other kind of integral we've done, it's a slice and refine kind of iterative process. It's just that the slices look different because we're using a different coordinate system. Ultimately, though, same basic strategy. All right, now you can't tell from how I wrote this, but I'm going to assert that when I wrote this all down, I followed my own rule. Let me get back up to here, which is always write this thing here all at once, because this is a good way to make sure you don't forget to insert that stretching factor. That stretching factor is super important. That's the most multivariable calculus of all the ideas that go into a question like this, is inserting that stretching factor. This is the recognition that you understand that there's a change of variables involved. This is the thing that requires some sophisticated work to compute. Everything else is mostly kind of plugging in and just doing geometry, right? So make sure to remember that it's usually worth quite a few points just on its own, right? So if you follow this rule, like I claim that I did when I wrote this down, right, and make sure to write this all at once, that will help ensure that you will not forget your stretching factor and that you will get those free points. You don't want to leave free, easy points on the table. How we doing? Everybody on board? All right. Now, notice how much I relied on the picture. The picture was essential to be able to draw the relevant conclusions of what do my slices look like? Where do they start? Where do they end? What surfaces are the endpoints on, etc. So you do need to have a good picture. I think this is a really big point. Try not to work off of a postage stamp size picture. A lot of students, I see little pictures about this big. Right? And oh my God, there's so much happening at such a small scale, and it's really hard to see. It's not just hard for you to, infer from. It's hard for your grader to figure out what you were trying to communicate with that picture. So try to make it good sized. I mean, maybe not the whole page, right? But third of the page, fourth of the page, perfectly reasonable. Right? Don't be shy about your picture. Go to the trouble to make a nice clear picture. You can use the pages at the end. You remember on the exam packets that I make, there's always at least 2 pages of scratch at the end. Practice. Do your bad drawings on the scratch, you may consider. And then once you have a good idea of what you're trying to draw a nice clear picture where your work is going to be. Don't try to do it all at once. It's very hard. Sometimes your first drawing will be bad, but it'll be good enough to help you have a better idea of what you're trying to draw, and then your next picture will be better. And possibly even iterate again. It may be that your third picture will be the one that's actually, okay, I can work with this. Right? In my travels, I remember one time many years ago, I had to go through that 5 times. My 5th picture was the one that was actually good enough to work with. Okay. All right. Lastly, there are things to know. Some people do, it would seem, have just natural talent at drawing things. I'm a little jealous, right? But you don't have to have the natural talent. What you need is to know what are the tricks. What are the techniques that make for a good 3-dimensional drawing, and then practice those techniques so that you get good at using them. This makes a tremendous difference in your ability to draw 3-dimensional drawings, even if you're not sort of just naturally inclined in that direction. Again, I don't consider myself naturally inclined in that direction. I use techniques and I have practiced, and that's why my drawings are, I'm not going to say they're great, right? But I think they're plenty good enough for our purposes. Okay, so give yourself those advantages. About the technique, I'll remind you, I've told you this previously, but I think it's worth repeating. Everything that I know about mathematical drawing, I've put into these videos in my miscellaneous topics playlist. Just go to my YouTube channel, look at the playlist. It's in there. It's called Drawing 1 and Drawing 2. I explain all of these tricks, and then I give examples showing how to use them and talk it through in gory detail. So I hope you'll find that useful. Okay, enough of that. Another example. Another ball, another offset from the origin with its center on an axis, this time on the y-axis. That's going to make things work out a little bit differently. Okay. Very first thing we do is we write down, of course, this whole thing, rho squared sine phi d rho d phi d theta. I have already scored a few points. Right, the very first thing I write down, write that one little thing down there, rho squared sine phi d rho d phi d theta. And you got several points in the bank. And you don't have to worry for the rest of the exercise, will I forget to write that down? Okay, starting with our theta slices. Again, this is what theta slices look like. Now we have to geometric appeal. You got to think about it. If you have a solid ball kind of, pressed up against the XZ plane touching the origin, and if you take an angled slice like that, geometric appeal, you're going to get a disc kind of like that. Does everybody buy that? Does that seem about right? Got to visualize that geometrically. By the way, if you have trouble visualizing, a good way to practice, a good way to help your way through, find some sort of actual physical balls. You can buy a sack of oranges if you want, right? And then think about how, okay, if I were to cut through, right, and you've got an actual visual aid, and you can think about, well, what do these slices look like? You could make your balls out of Play-Doh, and then you can actually cut them and see, okay, this is what that cut looks like, and then reform it and do other things that you might need to do with that. So something to think about. So let's think about first and last, and I claim, it's a matter of looking at the picture again, that x equals 0 is going to be where we'll start. It goes all the way around, well, halfway around, I guess I should say, and then it's going to end when we get over to x equals pi. And any angle theta that's between 0 and pi is going to, well, to some extent, it's going to kind of cut into that ball. And any angle that's less than 0 or any angle that's greater than pi is swing and a miss. Not going to cut through it at all. Everybody with me? All right. Now, as per usual, we redraw our theta slice. A little bit easier to see what's going on there. Let's see here. Now we're going to think about phi slices. Phi slice is something like so. Keep in mind phi is this angle measured off of the positive part of the z-axis. So where's our first and where's our last of these? First one straight up, where phi is 0. Good geometric appeal, right? This theta slice is a disk. Disks are tangent to the vertical axis there, and so straight up, anything that starts to lean toward the right, if you will, of straight up is going to cut into that disk. And then last slice straight down, which is pi. Pause for questions. Feel free. I mean, again, this is just we're kind of just doing a lot of geometry here, just to see what these things look like. Everybody's happy? Okay, and then, as usual, now we focus on a phi slice of our theta slice. We're going to look just at that sort of line segment thing. Rho starts there, right? Our next variable is rho. Rho starts there. Keep in mind that's actually, in our original picture, right, our little phi slice of our theta slice is something like that. This rho that we're starting at is actually there, which is the origin, which again, rho equals 0. And we're going to end, so our last value of rho at that point, which of course is actually that point, which of course is on our sphere, which again, and some tedious little detail that has to be done here, but you got to find the equation of that sphere. You take your given particulars, you write the rectangular equation, you convert a la chapter 1. That's the equation of that sphere. We're looking for a rho bound, so you solve for rho as a function of phi and theta. Conveniently, it's already in that form. And there you go. What do you think? Everybody see the process? Any questions about the geometry or the process? Okay. All right. Okay, here, let's see here. And by the way, make sure that you can do that, right? I mean, so I'm making a reference, as chapter 1, etc. But on an exam coming up, right? We've got about a week here. On an exam, even though this is something you would have done back in chapter 1, it's something that you need to be able to do for questions like this. So make sure that you're polished up on those skills. Okay. All righty. This last one is mostly a geometry example. Let me say that differently. More of an art example. So we've got a really weird looking solid here, and there's a particular point that I think makes the art quite a bit easier. So first of all, let's talk about our solid. We are looking at a ball here. Less than or equal to 1, so the radius is 1. And then here, now this is weird, greater than or equal to 1. It's tempting to say that we've got a ball, but when I say that it's we're x squared plus y squared plus z squared greater than equal to 1, what this is saying is I'm looking for points outside of the orange ball. Inside of the green ball, outside of the orange ball. And so altogether, what I'm actually interested in here, my actual solid, this is weird to draw, but it's kind of this thing here. And this is a bad picture for a couple of reasons. Let me get rid of the distractions. Because the thing is, there's actually kind of a lip down here, and now I'm sort of torn. On the one hand, I would like to fill in all of this, because after all, I mean, this lip does really come down to there, right? But now it looks like it's sort of solid all the way in between, but it kind of isn't. There's a pretty significant indentation, right, where this bottom sphere kind of takes a cut out of the bottom. There's a kind of a dimple, kind of a, I don't want to call it a cavity exactly, but there's a significant empty space between the front side of this lip and the back side of that lip, around the back side of it. It's hard to draw, right? Does everybody see what I'm talking about? Okay, well, and now, of course, I've got to take theta slices of that thing, and if it's hard to draw, then it's hard to visualize, and if it's hard to visualize, it's a little confusing to think, okay, what do these cross-sections look like? So let me show you the artistic trick. I think this is a really nice little trick. It's what I have listed here. Cross-section of an intersection is the intersection of the cross-sections. And I'm going to walk through what we mean by this here. First of all, let me persuade you that what we're talking about here is, in fact, an intersection. This thing, however it is I choose to draw it, however imperfectly, that's an intersection of sorts. Now, in this case, it's what's inside of this ball but outside of that ball. Another way to say that is it's the intersection of the interior of this ball with the exterior of that ball. So I'm going to use the word intersection interpreted like so. Okay, and I want to take a cross section of it. Right, so here's my sort of theta slice. That's what I want to figure out. So I'm claiming that what I can do is look at the individual cross sections first, right? So I'm gonna look at the individual cross sections. In particular, this first ball, it has a cross section, a theta cross section, and that's actually pretty easy to visualize and pretty easy to draw. If I take a theta slice of this, it's just a ball, right? Well, a theta slice of that is a half a disc, as I've drawn there. That to it. And then likewise, if I look at this other ball, let's think about its cross sections, right? That bottom ball, its cross section, same thing. It's a ball. It's nothing more than a ball. And the theta slices of it, again, half a disc, like this. And what I am interested in is the intersection of those individual cross sections. Now, this intersection game is easier to play. I just want to know what is inside of the orange half disc, but outside of the green half disc. And all that's left is what I have shaded in gray here, which now I'm going to outline in, well, I'll go ahead and shade it in purple. It's just that right there. So much easier to draw, right? I didn't have to visualize the actual sort of, oh golly, this thing's hard to see and hard to draw. Yeah, this bypasses that completely. The cross sections themselves are easy. The intersection of those cross sections, not that bad. Pictures right there. Everybody see the move here? I think this is a really nice move. And that gives me what my cross sections look like. And then, of course, you proceed and think about the range of values of phi and stuff like that. Okay, so I just wanted to show you all that little artistic trick. All right. By the way, good exercise here to think through the rest of these details. I will point out that this point right there, sort of the tip of the claw, if you will, that point, notice, is part of an equilateral triangle. That comes up again. This comes up surprisingly often, right? It's always something to be on the lookout for. So very convenient then to figure out what that angle is, right? That angle, well, it's just pi over 3. So. All right, make sure to think through the rest of the details, and we're going to move along. Okay. So, symmetry theorems. I'm going to start with some single variable calculus. Now, I've done the following move several times. I'm going to do it several more times throughout the rest of the semester. Excuse me. Sometimes the best way to segue into a multivariable idea is to start with the single variable equivalent. And I'm a big believer. Here is the single variable equivalent to something we're going to extend to multivariable. This is an old theorem. You've seen this before, I feel sure. And that is, right here, that if you have a symmetric domain over which you're integrating an odd function, then that integral is 0. Now you may have seen this written differently previously. You probably saw the integral written as integral from negative a to a, f of x dx. And that's what I mean by a symmetric domain. Let me explain what I mean by symmetric domain. I want to highlight negative a to a is a symmetric domain. If you were to draw this thing, and here's your x-axis, here's 0, negative a to a, notice that this interval, whenever you reflect over the origin, right, if you just flip it over the origin, it's what we call a reflection. Reflecting it over the origin, you get the exact same interval back. This interval is its own reflection. Does that make sense? So that's what we mean by a symmetric interval. It's a symmetric interval. You can say it as if a point is in the interval, then its reflection is in the interval. Take your pick. And of course, I hope you remember this definition, what an odd function is. An odd function is a function that has this feature motivated by odd powers of x. When you reflect the input, you negate the output. Right? So x cubed does this. Right? X to the 7th does this. Any odd power of x. Okay, so familiar? I hope this is familiar. If not, I think it's an easy pitch. Let me make the pitch. Here's why, one way to think about why this would be true. And let's see here. I've already forgotten what colors. Let's see, green for the domain. So here's our symmetric domain from negative a to a. And because it's symmetric, any point over here, which of course corresponds to a term in the Riemann sum. That's a term in the Riemann sum. There is a corresponding point, its reflection, a corresponding term in the Riemann sum here. Right, because it's symmetric, these little slices kind of pair up. And then because of the oddness, now keep in mind, odd means that f of negative p equals negative f of p. You write that down, and then you realize, well, that means that these two terms are negatives of each other, and two terms in a summation that are negatives of each other will cancel. So all the terms pair up and cancel, and you're left with this integral being 0. Yeah?
Is this the same reason why in one of the exercises in the book, for this homework, there was, I think, you're deriving x, you're integrating x in the interval 1 minus 1, and it just becomes x to the power of 2 it becomes 0.
I'm not exactly familiar with the reference you're making, but if it is, the integral. So x is an odd function, and if it's from -1 to 1, then that is a symmetric interval, and so therefore that integral should be 0. And now the way you might see it in a case like that is that the antiderivative, you're going to be subtracting the same value. And so you get 0. That's what I'm going to call sort of how the algebra works out. I would say this is more so why it's true, why it should work out that way. Is that satisfying? Yeah, totally. All right, now here's a different take, just a different point of view on why does this theorem work? Why is it that if you have an odd function on a symmetric interval, why is the integral 0? This is a change of variables argument. Now remember, we're still one-dimensional for the moment, thinking just on the x-axis. So change of variables is just a substitution, and we're going to make this substitution right here that x is just -u. Real easy little substitution. X equals -u. Nothing to it, right? It's a matter of kind of writing it down, etc. But since we're thinking of this as a change of variables, we're going to think of this g of u equals -u is the change of variables function. Okay. Well, that said, if we want to compute this integral, first, I'll take advantage of the fact that our domain is its own reflection. That's what we mean by a symmetric domain. It is its own reflection. So nothing happened between these first two integrals. Here, I'm just doing a pullback. I'm recognizing that I've got a domain that is an image. Remember, that's our big condition. If you want to be able to do a change of variables pullback, you need to recognize your domain as being an image of something else. Here, it's an image of itself. Right? And then you plug in x equals g of u. That's just the plugging in part. Don't forget your stretching factor. We're doing reflections. Nothing gets bigger or smaller with reflections. Reflections preserve size, so our stretching factor is 1. And then you notice oddness tells me that f of g of u, g of u is minus u. That's the formula. But f of minus u is the negative of f of u. Because oddness means that reflecting the input negates the output. So the nice punchline then is that this integral is the negative of itself. And there's only one number that is the negative of itself. That's 0, right? And so that's why we know that the integral is 0. Now, it's just a different take. You might like the Riemann sum take better. In some sense, it's a little bit more intuitive. But I kind of like the algebraic sort of simplicity of this argument as well. And by the way, this is why I do this material in section 5.5. It's because it literally, change of variables is a nice way to see it. So it fits in with this change of variables section. Okay. Alrighty. Let's extend this to 2 dimensions. All the same ideas. Let me go back up to here real quick. All the same ideas. We're going to have this idea of a reflection reflecting over a point in 1 dimension. Well, the analogous idea is reflecting over a line in 2 dimensions. And reflecting over a line, it's exactly what you think it is. It's just what we have in that picture there. Now here's the good news. This could be any line. Right? In some sense, we have kind of more room to move around in 2 dimensions. So, there's really, in some sense, only one way to reflect. You only have one direction in 1 dimension. Here we have lots of different directions, and so there's lots of different lines that you can talk about reflections over. Any reflection line will work. And then we make the same sorts of definitions. Odd means that reflecting the input negates the output, just like in single variable. Symmetric means that it is its own reflection. It means if you reflect the set, you get the exact same set. And we get the same theorem. Exact same theorem. Different particulars, morally equivalent. If you have an odd integrand integrated over a symmetric domain, that integral is 0. And very, very powerful tool. What this says is, this integral on the left, now just keep in mind, how do we compute integrals? How have we computed integrals in the past? Well, we've taken our domain and one way or another, we might do something clever like a change of variables in advance, but eventually we're going to have to start slicing that up. We're going to make an iterated integral, and then we have to do antiderivatives and use the fundamental theorem of calculus, which can be tedious and, oh my gosh, lots of effort, right? What's nice here is I just have to check a couple of conditions and then, boop, 0, done. Walk away. No anti-differentiating. No slicing and dicing. We just, a couple of clever observations, boom, integral 0. Okay. All right, now, it is a powerful theorem. It is totally awesome. I am a big fan, and I encourage you to use this theorem, but be warned, there are a couple of landmines. You do have to make sure that you check both conditions. I've seen the following happen a bunch, and as you all know, when I see a certain kind of mistake on exams, I like to make a big deal out of it in class to hopefully reduce the number of future such mistakes. I've seen it happen a bunch of times that students will look and find themselves a symmetric domain and get a little too excited about it being a symmetric domain and then just declare the integral to be 0, and they forget to check. That only works if the integrand is odd also. So don't forget, you've got to have both conditions for this argument to make any sense at all. And then furthermore, it's got to be the same line for both of these symmetries. Odd over one line, symmetric over a different line, no good. It's got to be the same line for both. Okay, now let's see why this is true. Well, the change of variables argument is exactly the same. If we have a symmetric domain, then it is its own reflection. An integral over a reflection is an integral over an image, and you can pull back. The usual pullback. And again, notice my stretching factor. When you're reflecting, it doesn't matter what line you reflect over. Reflections always preserve areas. So the stretching factor is always 1. So that's easy. Oddness means that when you reflect the input, you negate the output. And again, we find ourselves with an integral that is its own negative, and therefore it's 0. So it's a practically stolen off of the previous page. Totally analogous argument using change of variables. Okay. Or if you like the Riemann sum take, and there's something very satisfying about this as well. By the way, forgive my art. That's surprisingly difficult. I'm trying to draw a symmetric domain there, specifically symmetric over this line. Then terms in the Riemann sum pair up. And then reflecting the input negates the output, which means that these two terms are negatives of each other, and if they're negatives, then they cancel. So, again, practically stolen off of the single variable argument. Is everybody with me? Everybody has really kind of the same idea, right? Okay. All right, so let's do one. Let's get one of these done in practice. And there are some details to be dealt with. Let's draw our domain here. This curve looks something like that. By the way, this is a flashback to single variable calculus. Lots of things to say about where did this curve come from. Make sure you can do this. How did I get this equation and make this curve? You want to make sure that you're good at that, right? If you have any questions about this, come talk to me in office hours. Happy to help, right? But you want to make sure that you are good at that. And then we have, of course, that curve is a lot easier to draw at something like this. And then you notice that our domain is this region in between. And I'm going to kind of wave my hands and say that's clearly symmetric. I mean, you can see it from the picture here. In particular, if you reflect over the y-axis, right? You reflect this shape over the y-axis, it is its own reflection. Is that good? Okay. Now, how do we do the reflection? This is going to matter. And let's see here. I'm going to try to tidy up my picture a little bit here. Okay, that'll be fine. How do we do the reflection? Claim this is the formula for the reflection. Keep in mind, if you're reflecting over the y-axis, this is what the reflection looks like. And now let's just think about this picture. Right, here's the y-axis, and here's a x comma y, and here's where you reflect to. Notice when you reflect, the y-coordinate doesn't change. Reflecting over the y-axis, right? The y-coordinate doesn't change. You can see that I've written that down in the formula for the reflection. The y-coordinate doesn't change. You can also see the x-coordinate of the reflection is the negative of the x-coordinate that you started with. Again, right here in the formula. And this formula for the reflection is going to come up when you check for oddness. Now, okay, odd, you remember you have to reflect the input. There I'm reflecting the input. I'm going to plug that into my function here. My function f. And if you, whoops, wrong color. If you plug in that reflection, you get that. You got to think about the details here. What this says is, when I plug into this function f, everywhere I see an x up here, I need to plug in negative x, because that's what the reflection did. That means you're going to get a minus sign attached to every x in this expression. You see that happens right here. Everywhere you see a y up here, you just plug in y, because that's, again, what the reflection does. And then you take that algebra and work it out, and as needed, as required, anyway. You reflect the input, and you negate the output. How we doing? Everybody happy? Okay, so we win. Game over. This integral is 0. So again, keep in mind the conditions. We have checked that the domain is symmetric. We have checked that the integrand is odd. Both of these conditions were satisfied using the same line for both. Integral is equal to 0 by symmetry. And let's just take a moment to appreciate how awesome this was. What would we have done without this symmetry argument? Look at this integral up here. Oh my gosh, look at that. That's outrageous. Right? This as an integrand. Oh my gosh. But I could probably, I don't know, probably is a strong word. Maybe you might be able to do that. I'm not sure. I'd have to start working it out, but at best it's going to be a beast. Right? And then further think about this y. What are you going to be plugging in for y when you evaluate the y integral? You're going to be plugging in x squared minus x to the fourth. You're going to have a quartic times sine x. Best case scenario, you integrate by parts 4 times. That's highly undesirable, right? This would be a nasty, nasty integral to compute. We instead made a couple of clever observations and declared victory. That's totally awesome. Very powerful method. Okay. All right. Now, I am a fan. I'm sure you're picking up on that. I want y'all to use symmetry arguments. I think it's great. Everybody does. It's, oh my God, so useful. But you do have to justify your reasoning. And I have a pretty low bar. I used to have a higher bar for this. I've lowered my bar quite a bit on what I want students to show me to make a symmetry argument. Well, if you're going to use a symmetry argument, you got to let me know that you're using a symmetry argument. So say you're using symmetry. You do have to actually carry the ball into the end zone. You do have to actually conclude that therefore the integral is 0. Again, low bar, right? So just tell me what you're doing, right? And then the smallest of additional requirements, you've got to tell me what the line of symmetry is for what you claim is a symmetry argument. Right? And then, of course, you have to be correct. I hope that's obvious, right? So what I have seen several times, and this is a tragedy, and I don't know, it's very frustrating. A student will see one of these situations where maybe the domain is symmetric, but maybe the integrand's not odd. And the student will say, hey, this integral is 0 by symmetry over the such and such a line. Well, the domain's symmetric over that line. But if the integrand isn't, this is not partial progress toward a solution. The integrand's not odd. There is no symmetry argument. This is partial progress towards a dead end. Does everybody see the problem there? It's not actually progress towards solving the problem. There is no symmetry argument to use. So take this part really carefully, right? I mean, there has to be a valid symmetry argument that you're making reference to. If not, you're making reference to something that doesn't exist. And it's not progress, and so it's very hard to give partial credit. To be very, very wary of that. And what that means is that if you're going to use a symmetry argument, and again, you totally should, you 100% should. Symmetry arguments are awesome. Think it through. You don't have to actually show that the integrand is odd, right? You don't have to show all of this algebra, but you'd better think through that it actually works. So maybe look up here at the integrand and think, okay, look, what I'm going to be doing, everywhere I have an x, I'm going to be putting a negative x. Okay, I can see how this minus sign that goes here is going to get cubed because that's the minus sign I want. This minus sign will get squared. Okay, that's going to kind of just disappear. And then this minus sign is odd. So yeah, look at that. It's going to work. Right? So think it through very carefully on your own. Make sure that you are, in fact, referring to a valid argument. You don't have to write the algebra down. You do have to be correct. So I hope that makes sense. If you would need any clarification on this, come and talk to me. One last example we'll call it a day. And I'm going to focus on a particular part of this example. Here's our domain. Make sure you can draw this picture. That's all single variable. High school algebra. That's not hard. Here's the integral we want to compute. Looking at our domain, I think I can see that there's a line of symmetry like that. Now again, make sure that's actually right. Okay. The question I want to focus on is, how do I do a reflection over such a line? And it's a tricky bit. A point here, x comma y, and its reflection here, whatever that's going to end up being. Notice these are not negatives of each other. Right? It's not just negative x comma negative y. It just, you can see in the picture, it just isn't. So how do we find that formula? And I have a favorite way to think about this. If you think about this point in terms of the arrow representing it, how that arrow reflects is not clear because it's angled and it's just, it's not clear, right? What is nice and convenient is that if you look at this and this, it's what I call a rectangular frame for this point. This green horizontal line segment reflects in a very nice way. That's a 45-degree line that we're reflecting over. So horizontal reflects to vertical. Nice and easy. This vertical blue line segment reflects to horizontal. And that makes for a nice and easy little picture that you can sort of read off of there. And this input point x comma y, the reflection, you can persuade yourself, is just negative y comma negative x. So nice little trick. Think about this rectangular frame. The rectangular frame reflects in a nice easy way, and then you just interpret what this reflected point is off of that simple geometry. And again, a lot of other details, think it through, etc. And we will pick up here next time. Y'all have a good weekend. See you on Monday.